Hello. We're going to be working today on page 11 of our Chapter 11 notes packet, which is all about miscellaneous trig graphs. The two types of trig graphs we're going to be looking at today are the inverse and the reciprocal functions. We'll start out with the reciprocal functions first. The reciprocal of the sine and the cosine and the tangent function are cosecant, secant, and cotangent. We've already learned that quite a while ago, but their graphs are really different than the original sine, cosine, and tangent graphs. So let's take our graphing calculator out. And what we're going to do is, if there's anything in there, clear it out. Make sure the mode, you've set the mode to radians mode. And let's just put in y equals cosecant of x. Cosecant is 1 divided by the sine of x. All right, so 1 divided by the sine of x. And then press the zoom, option 7, trig function. And you can see coming up that there are 4 parabola-shaped graphs, and that matches this. But there are some things that our graphing calculator doesn't show on here that I'm going to have you add to this graph. So let's just move on to the secant graph. 1 divided by cosine, just change sine into cosine, and you can see that this graph will be the same thing as what you have in your notes. Exactly. And cotangent is 1 divided by the tangent graph, which kind of looks like a regular tangent graph, except it's been reflected vertically and shifted a little bit. So those are the first 3 we're going to look at. But what these things are lacking is a lot of stuff, actually. You should put arrows on the ends of all of these parabola shapes because they actually go up and down forever. That's the first thing. The second thing is, I would like you to, if you have a colored pencil or something different color, I'm going to have you sketch a sine curve, not 1 divided by sine, but just plain old sine curve on the same axes. And a sine curve starts at 0, 0, and it goes 0, max, and the max will actually touch this parabola. 0, max, 0, min, 0. So we can just draw a cute little, quick little sine function, and let's just label this y equals sine of x so we're not confused on what it is, and then go backwards. 0, min, 0, max, 0. So here's our little sine function. And what you notice is that because 1 is the reciprocal of 1, when the sine of x is equal to 1, which is at 90 degrees and negative 270 degrees, then 1 divided by 1 is still 1, and that's why they touch there at the y equals 1 line. Well, because this is a 1 divided by sine, you know that whenever the denominator is equal to 0, when sine of x is equal to 0, this becomes undefined, 1 divided by 0. So anytime the sine is equal to 0, it's where it touches the x-axis. Here, sine is equal to 0, actually 5 times on this graph. And what we're going to do is we're going to put in vertical asymptotes. So just put in dotted lines here, wherever the sine function goes to the x-axis. There are actually 5 vertical asymptotes. And down here it says it's undefined at x equals 0 because the sine of 0 is 0, and the sine of pi is 0, and the sine of 2 pi is equal to 0. So all these dotted lines are where they're undefined. And so what I'd like you to do is write in what they're really called. They're really called vertical asymptotes, these dotted lines. And the vertical asymptotes are at x is equal to 0. That's the y-axis right here. Here's the x equals 0. X equals pi, and x equals negative pi. So we'll just put plus and minus pi. X is equal to plus and minus 2 pi because that's this dotted line, and this dotted line are the negative and positive 2 pi's. And you could go into x is equal to plus or minus, I'll put an n for any number. 3 pi, 4 pi, 5 pi, any number that you put in there. So those are the vertical asymptotes. Now the domain of this function, remember we're looking at the cosecant function, which is these parabola-shaped things. The domain is the same thing as the domain of the sine function, which is all real numbers, except for The numbers that are not in the domain are these dotted line x values. So all the real numbers except for x is equal to 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, plus or minus n pi. So all the real numbers, you can name any real number and put it in for this x value, except if you put in any of those numbers, it'll become undefined. And then we'll talk about the range. So if you look at this parabola shape thing, let's just take a look at the range. It'll be easier on the graphing calculator. Y is equal to 1 divided by sine of x. Well, the range of this function is the y values. Well, the y values start at y equals 1 and goes up forever. And it starts at y equals -1 and goes down forever. But all of these values in between positive and -1 are not included in the range. So there are a lot of different ways you can say what the range is for this. I'll just say that the y values are greater than or equal to 1, which is the top half of it, and y is less than or equal to -1. Or you could have said all real numbers except y is between negative and +1 if you wanted to put an exception phrase in there, but this is good enough for that range. So that's it for the cosecant function. Now the secant function is very similar to the secant function, except it's the reciprocal of the cosine. So what we're going to do is we're going to graph a little cosine function in here, which starts at max 0, min 0, max 0, min 0, max. So we'll just write in y equals cosine of x, and we'll put in little arrows on the top of all these parabola shapes because they go down and up forever. And we're going to put in our dotted lines in between the U-shaped curves. These are all the asymptotes. So these curves get really, really, really close to these dotted lines, but they're never going to touch them. So it's undefined at all of these dotted line values. Well, these x values, I didn't put them in here on this little graph. I guess it was too small. But this is pi over 2, and this is 3 pi over 2, and this is negative pi over 2, and this is negative 3 pi over 2. So these vertical asymptotes, I'll just label them as a VA, vertical asymptotes, are x is equal to positive and negative pi over 2. That's these first two. And x is equal to positive and negative 3 pi over 2. That's this one and this one. And if you could go on and on and on forever, you could say x equals positive and negative 5 pi over 2. And hopefully you see the pattern. It's 1 pi over 2, 3 pi over 2, 5 pi over 2. It's all the odd multiples of pi over 2 are not in the domain. So if you wanted to write out what the domain is all real numbers, because you can actually go on and on and on, left and right forever, except for those odd multiples of pi over 2. That's where the dotted lines occur, the vertical asymptotes. And the range is the same as the range of the cosecant because it starts at -1 and goes down. It starts at +1 and goes up. So we'll just put the range is y is greater than or equal to 1 and y is less than or equal to -1. So that should finish that up for the secant graph. Now the cotangent graph. The cotangent graph, just like the tangent graph, it has asymptotes in between each cycle. So here's a cycle right here. And let's just put in our dotted lines here. And we won't graph a tangent graph right on top of that. It kind of gets confusing if you have a tangent on top of a cotangent. We'll just leave it alone. And all of these dotted lines are the undefined parts. Here's x equals 0. Here's x equals pi right here, this dotted line that we just put in. Here's x equals 2 pi. I didn't put in this last one in here. X equals 2 pi is this one, or x equals negative pi is back here. So the x values, or the vertical asymptotes here, are the same thing as the vertical asymptotes here. And that's because the cotangent, which is 1 over tangent, that's how we could put it in our calculator. Or we could also call this cosine of x divided by the sine of x. That's just another way of saying cotangent. And so wherever the sine is equal to 0, that's where you get a dotted line. Just like over here, whenever the sine was equal to 0, that's where you get a dotted line. This is the denominator going to 0, the denominator goes to 0. So we'll just say the VAs, the vertical asymptotes, are the same as y equals cosecant of x, vertical asymptotes. They're the same thing. And because the vertical asymptotes are the same, so that means the domain is also the same. As the cosecant of x. Now the difference in the cosecant in this one is, oh, we haven't put our arrows. Put our arrows on the ends of all these cycles. I guess we've got 4 different cycles here. The range is, there's no break in here. Remember there was a break in these other 2 graphs. There's no break in here. So this means the range is all real numbers. Y can be anything. Now these next 3 have nothing to do with the ones on top. These are arcsine. Arcsine is not anything like the cosecant, and they're put in the calculator differently also. So clear out the old stuff. We're going to put the arcsine. Arcsine is second sine of x. So when you press second sine of x graph, it gives you just this little tiny part of a graph, and we'll see on the next page we'll see why it is, why it looks like it does. And the next one is y equals second cosine of x, and that's another different looking thing. Actually, the arc cosine of x should go down and touch the x-axis. This graphing calculator has something wrong with it, and all of them do actually. This should actually go down and touch that right here. And then y equals second tangent of x looks like it does over here. I shrunk the window down a little bit on your notes. So there's your arctangent. So why do they look like they do? We're going to add some notes down at the bottom, but there's an explanation on the next page, on page 12 of your notes. So we're going to see why the inverse trig functions look like they do. Now I'm going to remind you, way back in chapter 4, we got the inverse of a function, and to get an inverse of the function, we just switch the x values and the y values, or the domain and the range. And then we get an inverse, no matter what. Switch the x and y. But there's another little caveat here. In order to have an inverse, the function must be 1, 2, 1. And if it's 1 to 1, it must pass the horizontal line test. It has to actually pass both the vertical and horizontal. But it has to pass a horizontal line test in order to be 1 to 1. So what I've done here is I've drawn you a little portion of y equals sine of x. This portion goes back to y equals negative pi, and it goes up to y equals positive pi. This is just a sine of x curve, but I've just shrunk the window down a little bit. And if you can see this, this sine of x is not 1 to 1, you can see, like, if you drew a horizontal line through this, it would fail because it touches it in both places. So this, looking like it does, it actually fails the horizontal line test. And so does the cosine curve, fails the horizontal line test. And we'll talk about tangent in a minute. So what we're going to do, because mathematicians had to get a graph of an inverse sine, what they did was they forced this to pass the horizontal line test by said, I'm going to forget about this part of the graph. I am just going to ignore this part of the graph starting at negative pi over 2 and to the left. And I'm going to start here, and I'm going to ignore this part, just cross it out. This is called restricting the domain. Instead of the domain being all real numbers, the domain is going to start here at x equals negative pi over 2 and end at positive pi over 2. So this right here, it's still a sine curve. This is still the sine curve. It's just been shrunk way, way down. And so now what we're going to do is I'm going to mark off what these coordinates are. This coordinate down here is negative pi over 2 comma negative 1. This coordinate right here is the origin, 0, 0. And this coordinate coordinate is x equals pi over 2 and y equals 1. So those are the three important points in what's left of our cycle. And we're going to now switch our x and y, which is the same thing as reflecting through y equals x line. If we were to draw a y equals x line, it would kind of come up like that. So now let's take each one of these 3 points and see where it gets us. So negative pi over 2, negative 1. Oh, what happens is we switch the x and y. Look at this. The negative pi over 2 and positive pi over 2, they were on the x-axis. Look, now they're on the y-axis. So what was on x becomes on the y-axis, and what was on the y-axis before moves over to the x-axis over here. Excuse me. So this first point right here, when you switch x and y, it becomes negative 1, comma, negative pi over 2. It's just the way that we mark our axes when we do inverse trig functions. This point right here is 0, 0. And this point right here is over 1 and up pi over 2. And then, just to get the direction that this should be, the concavity of this, it's called, this is called concave up because it kind of hollows down, and this is concave down. So if you reflect this through the y equals x line, this concave down becomes a concave up. It was a bump down, now this becomes a bump up. And then this other part was a concave down, and this becomes concave up. So that's why it's kind of shaped in the opposite direction. It's because it's a reflection through the line y equals x. Now we're going to do the same thing to the cosine graph. We're going to ignore part of it because this fails the HLT. So we're going to force it to pass the horizontal line test. We're going to stop it right there, and we're going to ignore this whole part of it, which means we're restricting the domain. We're making the domain start at 0 and end at pi. And then we're going to look at the cosine curve that only goes through this part of it. So it's going to start here at 0, 1. It's going to go through this point, pi over 2 comma 0, and it's going to actually end here at going over x equals pi and down to negative 1. 3 important points. So again, we're going to switch all of our x's and y's, which means on the y-axis, we're going to put the pi. We're going to put pi over 2. You should mark that in. And then here's 0 down here. And then on the x-axis, that was what our y-axis had on it. So now we're going to just put in those, reflect all of those points. This point right here is negative 1, comma, positive pi, which is this point down here. Switch the x and y and it becomes this. This point right here, you switch the x and y and you get 0 comma pi over 2, which is this point right here on the y-axis. This is over 0 up pi over 2. And then this important point here is over 1, 0, which was 0, 1 in the beginning. Now this is 1, 0. And then again, this is concave down, becomes concave up over here, and this is concave up and it becomes concave down over here. So that's why the arc cosine graph looks like it does. Now on the tangent graph, this is just one cycle of a tangent graph. Well, one cycle of a tangent graph actually passes the horizontal line test. So we're just going to start, we're going to restrict our domain to be x going to from negative pi over 2 to positive pi over 2. And if you remember the tangent graph, it had vertical asymptotes here. This was x equals negative pi over 2. And there's a vertical asymptote over here, which is x equals pi over 2. And then there are a couple more important points here on our tangent graph. Right here, this is exactly halfway. This is 90 degrees, so this is 45 degrees if you want to think degrees. 45 degrees is pi over 4. So pi over 4 comma 1 is important. And over here, right here, it goes through, this is negative 90, so this is negative 45 degrees, which is negative pi over 4. All right, so this point down here is negative pi over 4 comma negative 1. So we're going to take all these things, we're going to take the 2 asymptotes, and we're going to take the 3 important points. We're going to switch all the x's and y's, and we're going to make an arctangent graph. So this, I've already given you the horizontal asymptote. See, this is a vertical asymptote over here on the original one. Well, the vertical asymptote becomes a horizontal asymptote, which is y is equal to negative pi over 2. And this up here, this dotted line, is another horizontal asymptote, which is y equals positive pi over 2. The x's became the y's. And so this point right here is 0, 0. This point right here is pi over 4 comma 1, or 1 comma pi over 4. And this point back here is negative 1, negative pi over 4. So you got 3 important points. Oh, you should put arrows on the end because this goes to the right and left forever, and these go up and down forever. Tangent graphs versus arctangent graphs. So now we're just going to finish this little video up here by just adding a couple more things which just talk about the domain. This has no arrows. Don't put arrows on either of these because this actually has a starting and a stopping point. So there's no arrows like there's going to be over on the arctangent. So here, the domain. What is the x value? Well, the x value starts at negative 1 and it goes up to positive 1. What is the range? The range of the y's. The range is negative pi over 2 less than or equal to y's less than or equal to positive pi over 2. No asymptotes. That's about it for that. Over here, the arc cosine graph, the domain is the same because it starts at negative 1 and ends at positive 1. So this domain is also negative 1 less than or equal to x less than or equal to 1. But the range is different because the lowest y value here is 0 and the highest y value is pi. So this has a little different range than the other one. You just say 0 less than or equal to y less than or equal to pi. And that's it for the arc cosine that you need to know. And then the arctangent, put arrows on the end here. Here are the horizontal asymptotes, y equals negative pi over 2 and y equals positive pi over 2. And so the domain on this is because it has zeros, they go on and on forever. It's all real numbers. And the range, it does not go any lower than this dotted line. It actually never even touches this, and this graph will never even touch this. So when you talk about the range, you can say it's negative pi over 2, just plain old less than y, not less than or equal to, because it'll never touch that dotted line, is less than or equal to pi over 2. So those are the important things that you need to know, and that's all you need to know about the miscellaneous trig graphs. Have a great night, and I'll see you tomorrow.